This is Vladimir from Mobatec. Welcome to our demo where we will use a real refinery section dynamic model simulation made in our experts tool called Mobatec Modeler to briefly show you how we can use a dynamic process model for real-time or accelerated simulation, product quality process parameter analysis, process shutdown and startup procedures, and process control tuning and optimization. This is dynamic model of a real refinery section, and in these green text objects you can see the steady state values of the process important parameters. Now we can start a real-time dynamic simulation of the process. We will choose a dynamic simulation type. We will set 1 second for the time step size, and we will set 1000 milliseconds for the calculation delay. By pressing Start Calculations button, we will start a real-time dynamic simulation of our process. Here in the simulation time box we can see the real time, so these are the real seconds. You can also observe the simulation time in the left bottom corner of the window. If you take a look closer to the process, we will see that the process is already tuned to match 99% the steady state of the real refinery section. So for example, if you check the density of the products coming from the top of the column, they are matched 100%. Also the average molecular weight is quite close. The pressure and the temperature of the top of the column, as we can see here. Here we have the maximal flow from the top of the column, which is okay. If you take a look at the bottom of the column, you can also see the pressure and the temperature of the model and the pressure and the temperature of the steady state of the real column. Also the density of the bottom product, which is matched almost 100%, and the average molecular weight. Now we can stop the simulation. Real-time simulations are used for high-fidelity process simulations, where model response should match the response of the real factory. For example, if we start the simulation again, and we turn off this pump by clicking on the button, now we can see that the flow of this pump is getting to the zero slowly, and our reflux flow is zero. We can see now that the temperature is going up as we are not cooling down the top of the column, and our product is also not matching the steady state specification for the top product. Now we can turn on the pump again, and it will take some time until the pump builds enough pressure to start the flow towards the top of the column. So you can see we have some oscillations, but in the end the flow stabilizes itself, and we have our designed flow to the top of the column, and now the temperature is going down again, and will reach steady state after a certain time, which should be the same time as in the real factory. We will stop our calculation now. Sometimes, on the other hand, accelerated simulations are needed. That is, when we are not particularly interested in the microdynamics of the process, but want to see what will happen after a certain time, so for achieving a steady state or similar. Some processes have very large time constants, and engineers and operators cannot spot these changes within their working shifts. These constants can last for a few shifts or even a few days. Accelerated simulations are very much needed to catch these kind of problems. Now, let's accelerate our simulation in order to come to steady state faster. We will set our step size to 20 seconds and start our simulation. As you can see now, 20 seconds step, and we can delay the delay, and our simulation is now going much faster. As we can see, we already achieved our steady state. We can now stop the simulation. Now let's talk a bit about how can we affect a product quality by using process dynamic simulation. If we are about to build a new plant, then we can use a model dynamic simulations to optimize the process and to optimize the equipment design for that process to reach the desired steady state. In this case, this model was built based on the data of the existing refinery section, so we had to have 30 tray column, 3 heat exchangers, 1 air cooler, etc. The model was built, fine-tuned, and validated against the real refinery factory data. Now we can use this validated model to change some process parameters to get the most out of our plant. We can change all non-physical parameters like pressures, temperatures, flows. Of course, we can make suggestions for physical parameter changes like number of trays or the process lineup. As in the model, we can experiment whatever we would like to see, while in the real life that is not possible, of course. In this case, we will dynamically change the feed tray position to see how the feed tray position affects the top and the bottom product. Before we start the simulation, let's take a look at the right part of the model. Here, we have made the process cash flow estimate. Here, we have the prices of the feed, the price of the top product, the price of the bottom product, price of the slops. This is when the top or the bottom product are not up to the specification, then they are sold as slops, which have much less price. We have nitrogen that we are spending, off gas is here, that is the vapor from the distillate, and we have a fuel gas that we use in our furnace, that's pure methane, to heat up the column. Of course, this is all done for the demonstration purposes, prices and everything, but we can see that we at the moment have a steady state profit, yearly profit of 10.6 million euros, let's say. So we will see once we change the feed tray, how will that change our steady state yearly profit, because the feed tray will affect the quality of our top and bottom product, and that will affect our yearly earnings. So let's adjust the position of the model a bit like this. And now we can start the simulation. We will use 10-second step. Start the simulation. And let's change the feed tray to the third tray. We can see here that our average molecular weight and density is changed, and that immediately we are making no profit. Actually, we are losing money, as our top and bottom products are not up to specification. If we go back to the 12th tray, which was identified as optimal one, we can see that our top and bottom products are up to specification again, and that we are again earning money with our factory. We can now stop the simulation. Let's again refocus the entire model into the picture like this. Okay. Now I will demonstrate how the process shutdown and startup procedures are performed in Mobatec modular process dynamic simulations. We navigate to Advanced and to Sequence subtab, as the shutdown and startup procedures or any other procedures operations in the process are defined, can be defined through sequences. We will now load sequences file, and here we can see that we have process shutdown sequence and process startup sequence, which is a bit different. These sequences are quite simple, as they are made mainly for demonstration purposes, but of course, once you have a high fidelity dynamic model of your process, you can test off all the possibilities. You can introduce as many steps within your sequence as you need, and you can identify the optimal sequence for shutting down or starting up your plant. Let's now start the process shutdown sequence, but before, let's set the simulation time step size to 1 second. Now we can start the calculations. Go to Sequences tab, select the shutdown sequence, and press Activate the shutdown sequence. As we can see, the furnace will be shut down first, then all the pumps, then the feed flow. So here we can see that the fuel gas valve is closed, so that furnace does not produce heat anymore. And we can see that the temperature at the bottom of our column is dropping. Now the pumps are turned off, and in 30 seconds after this step, which is defined by the user, the feed is closed, which is this valve. So we have no feed anymore. We still have full column, so we have the top product because the temperature is still high in the column, and we'll need some time to cool down, which will take a lot of time, so we will not wait for that, but we'll select the startup sequence. First we have pump 706A starting, then the other two pumps, then the furnace startup, then the feed supply, and the off-gas valve. So we will activate the start up sequence. We can see that the pump 706 is on. All other pumps are on. Furnace is now getting the fuel gas, which needs to burn to produce the energy to heat up the bottom of the column. We can here see that the temperature is rising. We will see as well, first the temperature is still dropping, but at some certain point the temperature will start to rise as it will receive the heat from the bottom of the column. I'll just wait for that moment. Here we go. The temperature is rising again. So now the process is slowly getting back to a certain steady state. Now let's stop the simulation. Now the process would probably get to a desired steady state, as the model was previously already tuned to operate in that steady state, but that could take a lot of time. In order to get to a steady state faster, and not by accelerating the simulation, we can use the process control. Now let's navigate to Control tab, and here we will load the predefined control configuration for this model. The controllers' names will appear here. If we select the controller, we can see that this is overhead level. This is the level of the tank D701, and we can see the process variable is called like this. We can see the manipulated variable, which is this valve, and we can see the set point is 1 meter for the level of this tank. We have 5 more controllers. All the valves which have yellow numbers are control valves, including the pitch of the air cooler. So now we will just start our simulation, and we can observe the valves are now working, the control is working. Here, for example, we have lower temperature than specified, which is 113, and the reflux control valve will close in order to get the temperature to the specified value. As we can see, that is happening. Now we have a slight overshoot and the controller starts to work again, opening the cold stream and again cooling the top of the column. And if we wait long enough, the temperature and pressure will come to a steady state specified values, and the control will do its job. If we take a look at the bottom of the column, you can also see that the bottom is still heating up. So we have the bypass valve, the pump around through the furnace is closing in order to get less heat to the bottom of the column, so this temperature should start to drop as it happened. Now, pressure as well, closing into the steady state values. We are now running a slightly accelerated simulation, so it's not real time. Of course, it will take some time too, but this is very close to real time. You can see the seconds just a bit faster than the real time. If we leave the control long enough, the control will manage to get the process to the steady state. We can now stop the simulation. So once you have a high fidelity dynamic model of your process, you can try adding controllers wherever you like, and you can try out different control strategies until you obtain the best one for your process. This was all for this demo, and I hope that you found it useful. Until the next video, stay dynamic. Bye.